Hey everyone, welcome to the walkthrough for homework 3 for BIOEN 335. Let's get started right away by just reading the question. Luckily, we only have one question for this homework. And you're given a one-page introduction, and I just took some snippets from that. So let's start from the top. Freezing isn't the only challenge in cryopreservation. Thawing can be just as difficult. A microwave oven seems like a nice solution since it deposits energy quickly and microwaves are non-ionizing radiation. However, water absorbs microwaves more effectively than ice does, meaning that the portion of an organ that has already melted will get warmer at a higher rate than the remaining ice, the opposite of what we want. I don't know about you, but when you put some frozen meat or anything frozen in the microwave, I'm sure this is not a culinary tip, but when you use the microwave, you think your item or meat is all fully cooked because outside it's really hot to the touch, but when you take a bite or cut into the middle of it, you realize that there's still a frozen chunk of ice right in the middle. And that explains clearly what this first paragraph means is that, water, anything that's more water absorbs that heat. And these questions get more into the concepts that we've learned in class that show this. Okay, so that's all that the first paragraph is saying. But let's jump into the second paragraph, which is really the key part here. The transmission of radiation through a weakly absorbing material, such as ice or water, can be modeled by Beer's law, the Beer-Lambert law. And this assumes that the rate of absorption, so the rate of absorption at a depth x, is proportional to the local radiation intensity, I of x, times an absorption coefficient. And that is often written as mu of A or alpha. We're just going to use mu of A for this course. So we're not going to use alpha or mu because we've seen mu in 325 and we just learned about alpha as the thermal diffusivity. So we don't want to confuse that with the absorption coefficient. So let's just use mu of A for this course. And then it says we can write a differential equation. But before we even get into that, let's really understand what this paragraph is saying right here. So if I were to draw my meat or any object, and then we're going to just model that as a box. You can think it has some width into the page. And we're going to note that our X is going downwards. So it's the positive direction is going downwards, okay? And now we have some radiation, microwave radiation, going downwards into this meat, and then it continues onwards through these layers of thickness, right? And we know that this the intensity of the radiation doesn't change through the air, right? It only changes once it goes through some object. So we're going to denote this as I naught, I zero, right? I naught, just the original radiation. And that means even at this x equals zero, it's still going to be I naught, right? Now the goal here is we need to find the intensity at some given x position. And that's what we're going to derive right now is the Beer-Lambert law and how we can find the intensity at a given point. So let's go into that a little bit further. So we've all seen this. This is a change in x. We're going to find this change in x right here and derive for that. So let's write out what we do know. So we know that the intensity at a given x plus delta x, and this looks really familiar to how we've been modeling fluid flow, heat transfer. It's exactly the same steps, right? So let's keep going. That means it's going to be at I of x, and then we need to find how much is being absorbed. And right here, we know the rate of absorption, right? So that's the rate. So we can say minus rate absorbed. And of course, our rate needs to be multiplied by the distance, right? Or the change. And here it's delta x. So what we're saying is, well, this is the original intensity at x. Then we lose some intensity due to absorption. And that is by a distance of delta x, giving us x plus delta x. So this is clearly just writing out an equation right here. But the thing is, right, what is the rate of absorption? It says that it is proportional to the local radiation intensity. So I'll write right here, rate absorbed. And the rate is equal to, right, first R, I of x, and it's timed, and I'm writing the coefficient in front just because it looks nicer, times the absorption coefficient, which is mu of A. Great. So that means let's plug in everything that we have here, and that's I x plus delta x, just copying it from above, equal to I of x minus mu of A times I of x times delta x. Great. So doesn't that mean I can just use this formula from now on and answer all the questions? And the answer is no, right? The answer is no. And why is that? It's because as we move in x, right, we actually know that our intensity, the local intensity, it's changing. This is changing. So that means our rate absorbed is changing with our position in x, right? So let me write that out. So this rate, mu times I of x is changing, as we move in the x direction. This is really similar to week 1 when we learned about finding that Q in cylindrical, right? When we had that changing radius, we had a changing cross-sectional area, which then changed our Q at that radius location. So that means we need to write something we're all very familiar with, which is an ODE, an ordinary differential equation. And let's not freak out when we hear that term because it really is just a simple way of writing an equation when a rate is changing with that position, right? Or what that with that variable. So that means therefore, write an ODE. And there's nothing fancy that we do here. We're just going to keep going with what we have from above. So I'm going to rewrite what we have right here. I x plus delta x is equal to I of x minus mu a times I of x times delta x. It's the exact same thing I wrote up there. Great. So that means let's move the ix plus delta x term over to the right-hand side, and let's move all of this over here. All right. So, and then I'm going to switch it over. So we have ix minus, when we moved it to the other side, ix plus delta x, and that is equal to mu a times I of x times delta x. And I'm going to divide both sides by delta x, and that means that's gone, right? And this looks really, really familiar. What is it? This is where we take the limit of both sides as delta x goes to 0. And we've seen here when it's x and then x plus delta x on the other side, that is the negative derivative. That is the negative derivative. So that is negative di of x over dx is equal to mu of a times I of x. And this doesn't change because there's no delta x here. So when we take the limit, it remains the same value. So this result, we all know it's the basic ODE that we can already know the solution to. And we know, as we talked about, the initial condition for this, I'm just going to write that IC, initial condition is I of x at x equals 0 is I naught, I0, right? Because we said that it does not change in the air and only when it hits that object. So it's going to be I naught. That means the solution to this ordinary differential equation is going to be I of x is equal to I naught by the initial condition times e to the negative mu of a times x. Okay, that is the solution to our ordinary differential equation. And this actually gives us the actual intensity at that position. So let me write that out too, because it's really important that you all understand what this means. It means that I of x is the local radiation intensity at a given value of x. And not only that, I'm going to also write this. Materials have unique values of mu of A. They have unique values of the actual absorption coefficient. That's what differentiates our materials and how well this energy is absorbed, as it talked about in that first paragraph, right? So this gives our actual radiation intensity at a given position. It's not talking about how much is absorbed or at how much is changed. It's just talking about that value of intensity when we're looking right at that position. Okay, so with that being said, let's keep going. So we have for a standard microwave oven, we can assume that the absorption coefficient mu W is 0.2 centimeters to -1. And that is for water, right? Mu W for water. And we have the absorption coefficient for ice or of ice is lower and highly dependent on temperature. But we are assuming that ice, mu ice, is 0.05 centimeters to the -1 power. So we have our values here. And for this problem, we are using a frozen liver for implantation. And liver is over 75% water. And so we will model it using standard. Okay, so we're using water properties, standard water properties. That's another assumption. And we're also assuming that we can use 1D rectangular coordinates. Great. So our x, one directional x that we drew up here, that works. And then we are going to compare the situation just before it starts to melt and where the top centimeter is thawed, but the rest is frozen. Okay, and we'll talk about that in a moment. And the answers will be ratios for at least the first two questions. So you may leave the I0, I naught as a constant, which was shown above. So I'm just going to highlight that. Answers will be ratios. As you walk through these problems, as you're doing these homeworks, as you're working on exams, it's really important to be able to mark up the question and understand each of the components, each of the assumptions you can make, because it really can determine what you get for your final answer. So let's start with that first question. And it asks, what is the ratio of the energy absorbed in the top centimeter? Okay. When it is frozen and to when it is thawed. And let's remember that it said frozen means it's just ice. And thawed is water. Water. And it also said thawed water in that top centimeter. And that also says top centimeter here. So that means that that first centimeter, 1 centimeter, is going to be water. And let's recall what we wrote about for the definition of I of x is that I of x, Ix gives the intensity. So it gives the intensity at a given value and given x value at that. So the question, however, is asking about the energy absorbed. The energy absorbed is not the intensity. So what is the energy absorbed? And you might have seen this word absorbed earlier, and you're right. We talked about the definition when we first derived this ODE as it's going to be this rate absorbed, right? That means that the difference between intensities. So the difference between intensities is actually the ratio absorbed. So this is X, this is what we're talking about at that intensity at that, maybe let's say at that 1 centimeter level. Then if we're trying to find the change, then at this next change, that's going to be the new value, and the rate absorbed is going to be the difference between those two values. Does that make sense? So that means the change in I of x gives the intensity change. It gives the intensity change, the change in the intensity. And that change in the intensity is the amount that was absorbed. Okay. So what does that mean here? That means, well, always we need to first see what the question is asking, and it's asking for a ratio from frozen to thawed. And it's really important to know what it's asking. So frozen to thawed. And what does that mean? That means the change in intensities gives us the energy absorbed. And we need to understand that usually when we write changes, we do final to initial. But here we need to remember that as we go down from the top, downwards, 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 what's going to happen to the intensity? It's going to be decreasing because the energy is being absorbed. So that means that we should write initial to final to know how much was actually absorbed. Okay, but also if you have both negative values in the numerator and denominator, it should cancel out still, but still it's important to know what we're actually trying to find here. So that means I of x at x equals 0 is our starting point, and we know that's I naught, but I'm going to let you fill that out. Then the new intensity is at x equals 1 centimeter. And the difference between that will give us the absorbed. I'm repeating it a couple different ways so you can see how this is working. And then we're going to write that exact same thing down here. And now you can see I wrote the exact same thing. So the question is, what makes these two values different? Right? We both know that these are they're both I naught, but what about these two values? What makes them different? And if you have the answer, it's going to be mu of A, because one's frozen and one's thawed. One is ice and one is water. And remember, we said up here, materials have unique values of mu of A, and we're also given different values of mu of A here. So just keep that in mind that it's not going to be the same. So we're getting an actual ratio here, okay? Let's move on to part B. So part B is asking, what is the ratio of the energy absorbed? So it's another ratio, always love highlighting, in the next centimeter. So it's really important. We're now going from 1 to 2. And then, which is ice in both cases. Okay, it's ice in both cases in this next centimeter. And then the top centimeter, meaning 0 to 1 centimeters, is water and to ice. So let's draw that out really quickly. So we have two scenarios. And then we have, right over here, we have radiation going downwards and downwards and downwards. And then same over here. Should have just copied and pasted. It's okay. Great. And we have also always label that coordinate system, x going downwards, positive x. And then we have x equals 0 centimeters, x equals 1 centimeters, and x equals 2 centimeters. Not meters, centimeters. Great. And it says when the top centimeter is water over here, and the top centimeter is ice. And for both, the second centimeter is going to be ice. So this is the scenario that's asking, and as you can see, it's the exact same one as above. Now we're just looking at that next centimeter. But one thing that's different here, one key difference, is the question. The question says, when the top centimeter is water, to when the top centimeter is ice. The ratio is flipped. It's now thawed to frozen, not frozen to thawed. So that's a small trick right there that can confuse you, but it's really important to understand the way these ratio questions are asking to make sure they're set up correctly. And not only that, but it's not asking for the total ratio of the energy absorbed, but it's asking for just that next centimeter. It's really important so that we're realizing it's from 1 to 2 centimeters. It's not from 2 centimeters or 0 to 2 centimeters, but 1 to 2 and that next centimeter. So that means we have to write this out carefully. And I will move this down a little bit here. Great. So that means we are starting at I of x at x equals 1 centimeters. And then we're going all the way to 2 centimeters. And then on the bottom, same exact thing. And my question to you is, what are the different values here? And it's definitely not that final value because they're both going to be ice. This is ice, right? It's going to be ice. But our starting values are going to be different because we have a change right here through water. And over here, we have it through ice. You can see that we have different materials, and you'll see that you can actually use some of these values from over here, and they should be very helpful there. Okay, so just keep that in mind. All right, moving on to the next question. I just don't want to give too much away. Now, suppose that a cup of water in your microwave absorbs 5 times as much power per milliliter as a block of ice does. Okay, so water absorbs 5 times as much power per mil, that's important, as ice. And then I noted that it's per mil, and it says in the next sentence, it might not always say that, but that's why you have to look carefully. Note that this is power per volume, so the exact size of the cup and ice don't matter here. And do you expect that the water will heat up 5 times as fast as ice? So when we look at this question, what is the key phrase here? What is the key phrase here? Give you just a moment. It's going to be heat up. It's going to be heat up. And why is that the key word? Because we know that there's heat transfer through heat flux. We also know there's Q generation, but also we talked about this week in quiz section about heating up an object through burning that Cheeto, heating that up, heating up water. You know, in the first 2 weeks, we didn't assume that there was any heating up when there was a fire behind our metal or wood door, or that if I had boiling hot water in my hydro flask, that my hydro flask itself was not getting warmer. But we introduced that this week. And heating up, we remember it's Q equals mCp delta T. And also to change in Q, right? It's not just the one value. And here's another great analogy, right? It's about, we're talking about a change in Q. And if we didn't have this change right here, right, that would be really similar to the intensities. And when we evaluate that, right, change, we actually see the amount absorbed. Okay, there's another analogy there, but this is similar, but not exactly the same analogy. Okay, and in quiz section, we derived. And if you were confused by this, I really recommend going back to those slides, understanding each of the slides. Please come to office hours if any of these parts were confusing. But we were able to go from this expression to dq over dt equals rho Cp times dt over dt. And what is this? What is this over here? This is the rate of heat energy change per unit volume. It's per unit volume. So let's try to think about this. We actually know the rate of heat energy change per our unit volume here. And when we rearrange this to dT over dt equals 1 over rho Cp times dq over dt. Okay. And we're not saying the rate of heat energy change per unit volume, dq dt. This is not talking about the power absorption, but we're more concerned with what the question is asking here. It's asking about the speed at which this water is heating up. And this speed is going to be simply right here, dt over dt. It's the rate of temperature change. And when I say rate, it's a time rate. How fast? It's by speed. And we have rho Cp over here. And we need to then understand that this value is definitely, it's influenced by rho, but it's primarily influenced by Cp, right? By Cp. So let's think about it. What is Cp of water? What is Cp of ice? And how does that change dt over dt? And you should be able to answer. Does this make sense? And why? Right? Why does blank heat up faster than blank by this, by everything we see on the screen here? Because we can use our logic and our reasoning to get to this conclusion, but we should be able to understand it through our heat transfer ideas and our concepts that we've been learning in quiz section, especially from this last week. It's a really amazing way to solidify what heat capacity is and how that really plays into dt over dt. Okay? All right. Let's move on to the final question. Final question talks about the absorption coefficient of ice just below the melting temperature is dramatically higher than the coefficient for ice below about -5 degrees Celsius. So that means right here we have alpha. Oh, sorry, not alpha. It's the absorption coefficient. Okay. So let's actually see here. Therefore, it is beneficial to raise the temperature of a frozen organ to near the melting point by immersion in water before freezing. And so we have absorption coefficient and we have of ice, we can say below negative, or we'll just say -5 is greater than mu of A ice um, below, we'll say below -5 here, right? And let's see what is mu of water is 1. Then, would you expect the organ to heat up faster, higher dt over dt? So that, again, solidifies what we just talked about in the previous section. Heat up faster while the organ is frozen solid, while it is partially thawed, or when it is completely thawed, right? And so we need to remember, completely frozen is going to be when it is more than below -5, right? More than below -5. And that is right over here, below -5, frozen solid. And we know that when it's partially thawed, it's here. And then we are going to see that mu of water is completely. And I believe the mu of water value is up here. And you can find that and use that over here and see what are those values. And then use that reasoning, use that same reasoning to understand what is it talking about when it heats up faster. It's not going to be about the exact same here, rationales here. Try to use some of these properties that we talked about up here. we want to see an explanation about that mu of A. What does that actually mean then when we're talking about the absorption coefficient, right? And how does this all play in, combine with CP, into something we talked about thermal diffusivity, right? Thermal diffusivity. We remember this dt value, recall, we solved for dt over dt in quiz section. dt over dt talks about temperature, the change in temperature over time. And we saw that it's impacted by a value called thermal diffusivity, which gives us the speed. The thermal diffusivity gives us the speed of heat transfer. And it's based on a ratio of rho Cp to K. So try to think about what does that actually mean and how does that play in to all these different concepts on this homework. This is a real challenge question. I do want you to spend some time thinking about this. That last question on that quiz section slide for week 3, I truly recommend trying to get through that and understanding what does thermal diffusivity mean? How does it impact the temperature profile? What does it, why does it matter in terms of how fast heat goes through the system, is transferred through the system? And what does it mean when something has a higher rho Cp, a higher heat capacity? So those are all just some questions I want you to just dwell on, try to understand. And I don't want to give too much away about this question. So really give this one some thought. Thanks. And I'm always available for help in office hours, or please send me an email anytime, and good luck.